Okay, we're going to get started then. Thanks everyone. So, good evening. I'm Rachel Selfridge. I'm head of engagement here at the University of Leicester, and I am delighted to welcome you all this evening and that you're able to join us. Festival of Change events really are truly global events with alumni joining us from all around the world. So, no matter where you are, I'd like to extend a very warm welcome to this evening's talk entitled Fuels, Plastics and Gucci Perfume: How Chemists Seek to Turn Captured Carbon into Useful Products, which is led by Dr. Sandy Kilpatrick. Thank you for being with us tonight, Sandy. So Sandy will be starting the talk very shortly, but before he does, there's just a few housekeeping points from me. Feel free to keep your videos on for the duration of today's event, but please do keep your microphones muted so that we can all hear Sandy. And as a reminder, you can find the microphone and camera button at the bottom of your screen. Please do post your questions for Sandy in the chat box. We'll answer as many as we can during the Q&A section towards the end of the talk. A quick reminder that to stay informed about alumni news and events, make sure that your contact details are up to date with us. And if you are a user of social media, then you can follow us on Facebook, Instagram and LinkedIn at Leicester Alumni. Feedback on these events is really important to us, so please do let us know your thoughts on tonight's event using the event evaluation form, which will be posted in the chat at the end of the event. We value all of the feedback that we receive, and it really helps us to shape our events and better support you as our alumni community. So thank you once again for joining us this evening. I really hope that you enjoy the event, and without further ado, it gives me very great pleasure to pass you over to Dr. Sandy Kilpatrick.
Okay. Hello everyone, hopefully you can hear me loud and clear. Welcome to this lecture entitled Fuels, Plastics and Gucci Perfume: How Chemists Seek to Turn Captured Carbon into Useful Products. My name is Sandy Kilpatrick. I'm a lecturer in inorganic chemistry at the University of Leicester, right here in the School of Chemistry. And it's great to see everyone. Hopefully we can have a discussion at the end of the talk. I'm just going to flip over to Hannah now, and just to check that the camera and mic are working on Hannah's side.
Hi, I'm Hannah, and I'm a second year PhD student in Sandy's group here at Leicester.
Okay, so today I'm going to talk about carbon dioxide, the molecule, and why it's important. I'm going to talk a lot about its chemistry, a little about its physics, and even less about its environmental impact. But CO2 is a waste product from chemical reactions, particularly man-made emissions from chemical reactions. And that's why it's a 1 teraton problem for our atmosphere. So I'm going to talk about how carbon dioxide can be captured and utilized using chemical reactions and the enormous challenges involved in these. And I'll introduce some of the research that we're doing at Leicester, making obscure metal compounds and studying their reactions with small gaseous molecules like CO2. And then we'll scale up and look at some of the state-of-the-art technologies which are coming out of industry right now to mimic photosynthesis and to use as much carbon dioxide as possible and try and convert it into more valuable products such as perfumes, hand sanitizers, vodkas, jet fuels, and more. But before we go on to the chemistry, I just wanted to first of all introduce the Chemistry Centenary Appeal, because the School of Chemistry first welcomed its students in 1925. And so in 2025, we're going to be having our centenary event. And I've set up a link here to our appeal. So this wouldn't be an alumni event without appealing for some of your money. So if you scan this QR code here, it will take you to our Chemistry Centenary Appeal. This is a way to support PhD students from a diverse range of backgrounds who are interested in studying chemistry to PhD level. And we've got lots of events coming up in 2025, including a special event here in the George Porter building in the School of Chemistry. So the first chemistry building was in the Charles Wilson. So chemistry was there in the right wing of the building back in 1925. And these were some of the labs that were used for the first students back in the day. They actually look a lot cleaner and nicer than our current labs. But the chemistry student moved to a different building. You can see in this picture, we've got our very first female academic, Florrie Shaw there, who was the academic admissions tutor who let in this young chap, Peter Atkins, to study chemistry at the University of Leicester. So we're hoping Professor Atkins will be one of our guests at the centenary event in 2025. And if we have any chemistry alumni joining the meeting tonight, please do reach out. Please do get in contact or post in the chat, and we'd love to hear from you. Okay, on to today's lecture. We're talking about carbon dioxide. Now here's a picture of carbon dioxide, the molecule. It's got a black ball in the middle, that's a carbon atom, and 2 oxygen atoms either side. So carbon dioxide is a linear molecule. And the reason it's a climate changing molecule is because it absorbs infrared radiation. So when it does absorb in the infrared, it vibrates in these ways. So we see that those oxygen atoms can vibrate in a symmetric fashion or in an asymmetric fashion. And it's that asymmetric vibration which leads to CO2 acting in the greenhouse effect. Our first experiment today is we're going to look at the physics of CO2. Now, if you have carbon dioxide in the minus 78 degrees, it exists as a solid, also known as dry ice. So solid carbon dioxide transfers from the solid state to the gas state without passing through the liquid phase in a process that's known as sublimation. So Hannah's going to show that now. If we move over to Hannah's screen.
Am I alive now?
Better.
Okay, so I've got a glove here and I'm just going to lay a lot of the dry ice in. And over the course of the lecture, you'll see the sublimation in the glove, and the glove will expand, and maybe we'll even see it pop.
So 1 meter cubed of dry ice weighs about 1,500 kilograms, depending on how much you compact it. So 1 meters cubed of gaseous carbon dioxide weighs only about 2 kilograms. So basically, we've got a 760-fold change in volume when it sublimes like this.
So I've got the glove, and I'll just make it.
So gases take up a lot more space than solids, and we'll show this by seeing as the solid carbon dioxide, dry ice, warms up, it expands, becomes the gaseous CO2, and we'll see that expansion taking place. At some point during today's lecture, there will be an explosion. Hopefully, yeah, you'll hear that at home, and hopefully Hannah won't jump out of her skin. All right. CO2 is a common waste product from our industrial activities. So we use CO2 as a fuel in our cars, in our combustion engines, to heat our homes. And basically the chemistry of CO2 in this equation is basically as a waste product. So when we burn fuel, it's a combustion reaction. The fuel, which is a hydrocarbon, combines with oxygen to release CO2 as the waste product and water as another waste product to give us the heat, which is what we're after in these combustion reactions. Now, why would that be a problem? Well, liquid fuel, so a small shot glass of liquid fuel takes up a very small volume. So 1 shot of liquid fuel, 44 milliliters. If it's completely combusted, it will lead to 112 pints of carbon dioxide because of that expansion from the liquid phase to the gas phase. So if you think about the sheer volume of CO2 that we're producing when we're burning a liquid fuel, 1 shot glass leads to 112 pints of CO2. So we're going to look at combustion in our next experiment, where Hannah's going to show what happens when we take a liquid fuel. In this case, it's going to be ethanol, and we combust ethanol in oxygen. So we're going to be looking at burning a banknote. So I'll switch to the camera, and Hannah will show you a dollar bill there. See Ben Franklin's face.
So I'm just dipping it in the ethanol.
You can see the flames. Yet the banknote doesn't burn at all. So you can see that banknote is absolutely fine. It's not even hot. So that's a result of the complete combustion of the ethanol, that hydrocarbon, but the banknote itself stays intact. So when we burn any carbon-based fuel, we produce CO2 and water. And humans exploit that in the combustion of fossil fuels to power our power stations and our transportation, and also our chemical industries like cement factories or aluminium production or fermentation plant. So if I switch back now, you can see same experiment carried out in a controlled lab environment, but luckily we were allowed to do this for you today. So you can see once again here, this is what happens when we burn that banknote. The ethanol is burning, releasing carbon dioxide and water, and crucially, heat. So why is this a problem? Well, increasing carbon dioxide flux into the Earth's atmosphere by fossil fuel combustion has not been balanced by an increase in intensity of our natural carbon sinks. So we've got a net increase in atmospheric greenhouse gas concentrations that affect global climate change, air quality, human health, and energy security. Now, I am not a climate scientist. This is about the extent of my knowledge of the greenhouse effect. But any of you who've studied GCSE geography will know that basically this works by the blanket of CO2 is going to trap the sun's energy within the atmosphere, leading to global heating. So you're aware that CO2 is one of the most abundant greenhouse gases on Earth, but there are other greenhouse gases which are important, like methane, like CFCs, like nitrous oxide. And these can all cause climate change by the same purpose. So why is this a problem? Well, if you turn on the news every day, you'll see some news story about climate change. CO2 levels on Earth have reached an all-time high, and mitigating man-made climate change is a defining challenge of our era. However, the global economy and our society are critically dependent on these fossil fuels, which meet 80% of the world's energy demands and feed the production of 95% of all chemical commodities that we rely on in our everyday lives. One of the catastrophic effects of climate change is ocean acidification. So Hannah's going to show you this now by showing what happens when we add carbon dioxide, dry ice, into a liquid to which she's added universal indicator. And this is going to show what happens, what takes place in our oceans when they absorb carbon dioxide, they become more acidic. So over to you, Hannah.
So loading in some indicator, and that will tell us about the pH of the liquid. A little bit of sodium hydroxide. So you can see it's gone purple already to indicate that the solution is basic. And then just topping it up with water.
So this universal indicator is a mixture of 4 different indicators, and it's got a pH range of 4 to 10. It shows the acidity of the solution with various colors. So this is a dilute sodium hydroxide solution, so you can see that it's in the alkali range.
Okay, and then I'm now going to put in the dry ice.
Let's see if we can observe a color change. When the fumes of CO2 die down, what's happening, not only is the CO2 subliming from the solid state to the gas state, but also some of that carbon dioxide is dissolving in the water. And as it dissolves, it forms carbonic acid that we saw in the slide. So this substance here, H2CO3, that's carbonic acid. It's an acidic substance, and therefore our universal indicator changes from the purple range when it's in the alkali range, down to through the neutral range, green, down to yellow, and ultimately red.
So let's go green now. Start turning yellow as it gets more and more acidic. There you go.
So this is a problem for the oceans because the ocean's pH value as of 2020 was 8.1. So it's currently lightly basic, but ocean acidification will result in a shift towards lower pH values in our oceans, meaning the water will become less basic, more acidic, and ocean acidification can lead to the decreased production of shells, of shellfish, and other aquatic life with calcium carbonate shells. So we'll see that in our next experiment, the effect of acid on oyster shells. So oysters, their shells are made of calcium carbonate, which is a solid substance. And when it reacts with an acid, it will dissolve to form calcium ions. And in doing so, it will release more CO2.
Okay, so what I have here is an oyster shell and some acetic acid, so mimicking the acidity of the ocean. And what you should see as I pour this in is our poor oyster shell starts to fizz.
And what we can see there, we've added acetic acid to our pint glass with an oyster shell inside, and it's starting to mildly fizz. So those bubbles which are coming off gradually, those are bubbles of CO2 which are being produced. And the effect of this is basically ocean acidification leads to calcium carbonate dissolving and releasing more CO2, which then leads to a feedback loop by which we then produce more carbonic acid, which leads to more shells dissolving, which leads to more CO2 being released. And we can see that in the systematic bleaching of oyster shells in the ocean. So this study showed over 40 days how a drop in pH in the ocean can change to have different effects depending on the degree of ocean acidification. So we can see at pH 8.1, we've got these brown oyster shells. At pH 7.5, which is more acidic, we've got this bleaching effect taking place. So what can we do about the CO2 problem as chemists? I'm going to show you three crucial ways in which chemists can fix CO2 in various chemical reactions. The first of which is mineral carbonation. This is one of the very basic reactions you can do with CO2. Pardon the pun for any chemists out there. So our next experiment is about carbon dioxide sequestration. So this is basically an industrial process in which CO2 can be fixed by reaction with a base solution. So what Hannah's going to show you now is when sodium hydroxide solution reacts with CO2. Now for any road bike, any cyclists in the audience, we've got one of these, which is a CO2 canister. So I'm going to release pure carbon dioxide into the bottle. And in doing so, demonstrate this reaction. So let me know when you're ready to go. So I'm filling the bottle with carbon dioxide. And because carbon dioxide is heavier than air, it displaces the air that's inside. And is sealing the bottle, and as it reacts, the carbon dioxide is sucked from the gas phase into the liquid phase, and that leads to a compression in that bottle. So what's happening there? The CO2 that was released reacts with the sodium hydroxide solution to form a solution of sodium hydrogen carbonate, and that's why the bottle itself will contract. This basic reaction is being used in the chemical industry to fix CO2 on a megaton scale. Mineralization, combining CO2 and cement production would be one way to withdraw carbon dioxide from our atmosphere and utilize it to make a more useful product of value. Another pathway for CO2 conversion occurs in biology, of course. So green algae convert CO2 into fuels like biodiesels or proteins like animal feeds. And these have gone beyond the proof of concept, and there are companies now scaling up these technologies. But one of the key barriers to biological CO2 conversion is the resource needs of the algae. They need space, they need water, and this is a key challenge to scaling up this technology. So plants, of course, green plants undergo photosynthesis reactions. So in this, carbon dioxide is a feedstock. So taking carbon dioxide plus water with sunlight as a source of energy and chlorophyll as your catalyst, plants produce carbon oxides as their fuel, as their sugars, and for building their bodies. Oxygen is a byproduct of this reaction in photosynthetic plants. So us as chemists, how can we convert CO2 into more useful products? Well, our research involves organometallic chemistry. This is where we have a metal atom sandwiched between organic ligands. And we use these organometallic compounds as catalysts. And we take inspiration from the biological systems that we talked about. We look at their active sites. We look at which metals are involved in the key chemical reactions. And we try in the lab to mimic those catalysts by making small molecule variants of them. This is a historical painting from Joseph Wright of the man who put the P into phosphorus. So this is a German alchemist known as Henning Brandt, who thought he knew the secret to making solid gold. So in the 1660s, he set about looking for the philosopher's stone. So many alchemists like Henning Brandt were looking for ways to turn base metals into gold. And so Henning Brandt's golden ambition was to look for the philosopher's stone. He dehydrated 12,000 pints of his wife's urine in a basement lab in Hamburg to try and make this happen. So he took 1,500 gallons of urine and he boiled it down, he boiled it down, he boiled it down, condensing all of that pee until he landed on a white substance which glowed in the dark. Now, Henning Brandt thought he'd discovered gold. He thought he'd discovered the philosopher's stone. And what he'd actually discovered in a surprise twist, he'd discovered the element that we now call phosphorus and one of the building blocks of life. And the reason I show this story of an alchemist who sought to turn base metals into gold is this spirit continues today. We're trying to turn waste products like carbon dioxide, things that are byproducts of our human activities and in our industrial activities, and upcycle them into more valuable things that we can profit from. To do this, we don't use alchemical techniques like the philosopher's stone. We're using highly sophisticated catalytic technologies that we develop in our chemistry labs. So ultimately, we're looking at ways we can turn carbon dioxide in the presence of a catalyst into useful industrial feedstock molecules like carbon monoxide, like ethanol, like methanol, and like formic acid. To do this, we use organometallic chemistry, as I mentioned. This is where we take an organic component, like a ring of carbon atoms, and we sandwich a metal in between this ring of carbon atoms. And these compounds are indeed known as sandwich compounds. Ferrocene is one of the most famous examples of this. So we do think about these molecules as sandwiches with a metal atom with a sandwich between organic ligands either side. So during my PhD research, our lab was looking into uranium sandwich compounds. So this time, the bread in our sandwich was based of these 5-membered rings and these 8-membered rings. And the meatball in the middle was a big fat uranium atom colored in green there. And we used some silicon-based shrubbery around it in order to protect that highly reactive uranium center. Now, if we look at these space-filling models, we can look at how the organic fragments around the uranium metal atom protect that center from the back view. So we look at that backside, we can't see any of that green uranium atom. However, if we look at the front end of the molecule, you can see there's a small amount of green surface which is poking through. And that is a reactive site in which small molecules like carbon dioxide can dock in and react. So we're controlling the space around the highly reactive metal center. So what happens when our uranium sandwich reacts with CO2? What we observe in this case is a reaction coupling two fragments of CO2 together between two uranium atoms. The overall reaction is called a reductive coupling. What we're doing is combining two CO2 molecules with two electrons provided by the uranium center to make a two carbon-based fragment in the center there called an oxalate fragment. So the oxalate is their sandwich between the two uranium atoms. Unfortunately, this is never going to become a catalyst because the bonds between oxygen and uranium are far too strong. However, it's a proof of concept to show that we can start linking up CO2 molecules together to form longer chains of carbon. How is this being done industrially? Well, there are existing chemical plants out there. For example, this one in Iceland, Carbon Recycling International, are using CO2 as a feedstock to make methanol, which is a key fuel for the shipping industry and is also often used as a chemical feedstock to make other platform chemicals that we rely on in our everyday. So this plant is actually making 12 tons of methanol per day, 4,000 tons of methanol per year, but that's still very small in the context of most chemical plants. So it's producing the equivalent of 15,000 barrels of oil or putting 2,500 electric cars on the road. What else can we make from CO2 that might be useful? Well, we're interested in using electrochemical technologies to try and convert carbon dioxide in the presence of protons and electrons, also with specifically designed catalysts to make alcohols, which are also useful compounds, not only for drinking, but also for the chemical feedstock. This is a process, of course, that biological systems can do in fermentation, in which sugars are converted into alcohols in the presence of a catalyst like yeast, and in doing so, they release CO2. But with our electrocatalytic technologies, what we'll try and do is use CO2 as the feedstock to make alcohols like ethanol. So what can we make from alcohols? Of course, ethanol is a key ingredient in drinks. So there is this air company based in the USA. Whoa! For those of you who didn't see it, the glove finally exploded. Hopefully you heard that. As I was saying, Air Company produce ethanol from CO2. So they make this vodka, which is about $300 a bottle. But nonetheless, every single drop of that vodka was produced from carbon dioxide, which was converted into ethanol. Since the pandemic hit, Air Company have also been using their ethanol in hand sanitizers, which are predominantly made of ethanol with some moisturizer added to them. And they also have a range of fragrances. And this idea has been taken on by the Gucci labs in Italy. They have this fragrance, Where My Heart Beats. It's their newest fragrance. And it's actually, rather than, it's been made with agricultural raw materials. And this is the first one to be used from alcohol, which is from 100% recycled carbon dioxide emissions. So that's a world first. And it's obviously a luxury product, which costs $330 a bottle for 100 ml of this carbon dioxide based perfume. But if you're interested, we do have a bottle of that here. Unfortunately, you won't be able to smell that at home, but it smells lovely. Okay, so what are we doing in our lab? I mentioned that we're inspired by biological systems. We're looking at harnessing the same metal atoms that are found in nature's catalysts, which are enzymes. And one of the key catalysts we're interested in is this carbon monoxide dehydrogenase enzyme, which has an active site involving a nickel atom, which is able to reduce carbon dioxide to carbon monoxide in a proton-coupled reduction reaction. So when we design our catalysts in the lab, we also look at using nickel as the key redox center for reducing carbon dioxide. And we're positioning two metal centers at close proximity in order to mimic what we observe in the active site of the enzyme, which is two different metal centers acting in concert with one another. showing cooperative effects in order to bind carbon dioxide and reduce it. What we found in my previous lab is that CO2 can be reduced by nickel centers, again, to form this oxalate species. But what was really key in this case is that the oxalate species could be transformed back into the starting nickel compound by using electrons, by using reducing agents. That's because the bonds between the nickel and the oxygen are much weaker than the bonds between uranium and oxygen. So we're able to now have the basis of a catalytic cycle by turning CO2 into oxalate and then breaking the bonds between the oxalate and the nickel and regenerating our nickel catalyst. And so what we're actively working on now is trying to do that instead of using a reducing agent, which is expensive. We're trying to use electrons, which can come for free from renewable electrical energy if they could be coupled with, for example, wind turbines or solar energy. So we're now working on electrocatalysis, which is using electrons to power this chemical reaction. So that's our current mission. We're looking at turning CO2 into useful products based on sustainable catalysts. As I mentioned, our catalysts have two different metal centers, and we select our metal centers using biology as an inspiration, but also looking at elements which are abundant in the Earth's crust and elements which are non-toxic, like iron, elements which are cheap and plentiful, like titanium, and elements which are utilized in biological systems, like nickel. And so these form the basis of the compounds that we design in the lab, and then we work on investigating their chemistry with carbon dioxide. We take enzymes as our inspiration for these catalysts. We look at the selection of metals that are used in those enzyme catalysts in order to select which are the best metals for redox reactions. And ultimately, our reactions require an energy input, and for any of this to be useful technology, the energy has to come from renewable electricity. So that's why we use electrochemistry as a way of powering our reactions in order to get catalytic turnover, which is in theory powered by renewable electricity. Okay, so that's the end of the talk. I'd just like to say thanks very much to people past and present who've contributed to the work that I've shown you today. So some of this was done at the University of Sussex, the University of Oxford, and the Humboldt University of Berlin. And the more recent work was done by my group here at Leicester. Thanks very much to Hannah for showing us the demos. Hannah, can you give us a wave? And if I just swap back, this is the current group here in Leicester. So we're a small team of PhD students and master students, and all of us are working on this design of catalysts inspired by nature with the view to reacting with greenhouse gases like CO2. So I've been lucky enough to receive support from these funding bodies over the years, and that's all for my talk. I look forward to your questions.
Thanks, Sandy. Well, that was really interesting. We've had a couple of questions come through, but I'm actually going to start with one of my own, if that's okay.
Can I stop sharing?
Sorry, Rachel.
No, you are still sharing. Bear with us.
Sorry, we're just turning the sound up on our end. Bear with it.
Okay.
Okay, Rachel, you okay to carry on?
Yeah. Can everybody hear me okay? Is that okay? Yeah. Yeah. Okay, perfect. Thank you, Sandy and Hannah. That was really interesting. The first question I'd like to ask is obviously both the vodka and the perfume that you mentioned, they've got quite high price tags, and I wondered what the reason for that was. Is it due to the process that has to be used to get them to that point, or is it just the rarity of them? What's the sort of the thinking behind those quite sort of premium price tags?
Yeah, so I mean, luxury products are always sold at a high premium, of course, so despite the fact that, a Gucci perfume is predominantly made from ethanol, which is a very cheap chemical, of course, the design of the perfume, the packaging, everything that goes into making that product a luxury product, why they can justify such a high price tag for any Gucci perfume, even one that's made from just standard ethanol produced from fermentation of sugars, for example. So it's not necessarily the CO2 technology which is leading to that being such a high price chemical. Ethanol is currently so cheap, such a cheap material, using fossil fuels or using sugars as the feedstock for it, that it's very difficult basically to produce it from CO2 at the same price. So that's a really key challenge to basically being able to outcompete these high volume bulk chemicals like methanol, ethylene, ethanol. Producing them at the same price will ultimately be what makes these technologies live or die. However, in the future, as our fossil fuel resources are used up, and also the impacts of climate change become so critical that we must leave fossil fuels in the ground, that's when basically it then becomes more expensive not to do more sustainable technologies like CO2 utilization at that point.
Sure, no, that makes a lot of sense, and obviously we perhaps wouldn't expect the vodka or the perfume to be sort of made in this way. Are there any other products out there that we might be shocked to know are using this as a technology?
Yeah, so one product that's being used is plastic. So you can make polyurethane materials from carbon dioxide. So Professor Charlotte Williams at Oxford, a very famous researcher in this area, her research, which is also on catalyst design, is about turning CO2 and epoxides into polycarbonate materials. And that research was so successful, it led to a spin-out company, which are now using that technology to make polyols, which are being used for things like fillers, I think, in walls. And ultimately they can make things like shoes, like the foam in trainers out of these polyol materials. So it's clearly has a commercial future. The company is still very successful, and I think there's a lot more interest from the chemical industry into like what can we make from CO2. So a plastic is a perfect thing. It's a carbon-based chemical, which if the carbon building block is CO2, then it's never going to reduce the amount of greenhouse gas, in a meaningful way to mitigate climate change. But it's about taking that waste product and upcycling it into something useful like a plastic.
Sure. So there's a question in the chat that's kind of follows on from that, I think, Sandy. So Jordan is asking, how close do you think we realistically are to using carbon capture on a scale that can make a difference to reversing global warming and heating, and what sort of period of time would you say we may need to start making a meaningful difference to global warming and heating via carbon capture?
I mean, personally speaking, I'm not convinced with carbon capture technology itself. So, carbon capture as a technology has existed for many years, and it's really, really expensive. And basically, if it was viable economically, it would have already been scaled up by now. So basically, like the carbon capture plants which exist are just like a drop in the ocean. In fact, I've heard people say trying to bail out the CO2 problem with carbon capture is like trying to bail out the Titanic with a teaspoon. The scale is far too big for something like carbon capture to be helping us out in that regard. And don't forget, carbon capture is just about burying the problem effectively, capturing the carbon and storing it somewhere as CO2. Carbon utilization is about having a a technology adjacent to that, which can then convert that carbon into a molecule that's more useful. So it's usually a multi-carbon molecule, like ethanol, like I showed you, like ethylene, which is a starting point for plastics, longer chain hydrocarbons. So you might have heard of e-fuels. Lots of car companies are really interested in this idea of e-fuels. So Porsche have a lab which is turning CO2 into fuel that you can run your Porsche on. Again, it's a really high-end product because at the moment the energy input and the research that goes into it is really expensive. So it's still a very financially intensive process.
Sure. Okay. Thank you. So Chris has asked, have you tried using aluminium as a catalyst?
Yeah, aluminium's a great shout. Obviously, one of the most abundant elements of metals in the Earth's crust, and there's a lot of really excellent aluminium organometallic chemistry that's happening in the UK right now. It seems to be, the real trendy element at the moment that's happening. So there's great research being done at the University of Edinburgh on aluminium chemistry. There's great work at the University of Imperial College doing aluminium chemistry. The traditional chemistry of aluminium doesn't have redox chemistry. So that's where you have an electron being transferred, which is ultimately what you need to reduce carbon dioxide. So carbon dioxide is the most oxidized form of carbon possible. And in order to turn it into something useful, like a hydrocarbon, you need to reduce it. And that process involves a gain of electrons. And so the catalyst needs to be able to give up those electrons. So actually aluminium traditionally isn't a redox active metal. And therefore it's not being used so much for these electrocatalytic reactions. However, some of the most cutting edge research is starting to disprove what I just told you. So I'm going to keep my mouth shut after that.
Fair enough, Sunny. Thank you, and thanks for your question, Chris. Getting a little bit more personal then, Sunny, what was it that made you want to be a chemist initially? What sort of drew you to the wonderful world of these bangs and explosions that you've shared with us tonight?
For me, I really liked chemistry because it was really hard. I think a teacher told me that it was really hard, and that seemed like a real just a great challenge at school when I was deciding which subjects to pursue. And I really liked the creative aspect as well. So I also enjoy music and enjoy creative endeavors. But I found like chemistry had the best of both. It had a lot of rational basis behind it, but also you had that chance to explore the world around you, to try things out in the lab that basically before you've tried a reaction, you can't really on first principles tell what's going to happen, particularly once you start doing research. You can read all the textbooks you like, but ultimately you have to be in the lab and test things out. So I found that a really a creative discovery process. So that drew me to chemistry. How about you, Hannah? Do you want to?
Yeah. So similar to you, actually. As a kid, just seeing science happen in front of my eyes was fascinating, and I think it's a great way to help people. And I don't sit at an office desk all day. I get to play with chemicals, and I think it's the process of research and the unknown. Like I go into the lab and I don't know what's going to come out at the other end, but I can try and see what happens and figure out that and move on. And it's an iterative process. So, we all work together, and I might find something out, my colleague might find something out, we put that together and you get the next big discovery. And I just think that it's a great way to live your life and help people, really.
I mean, hopefully the message came across that it's a real team effort, working in a research group for chemistry. So, everyone's feeding in ideas, people are working on multiple projects, which is all towards this grand aim. And also it's a highly competitive process. So, I've shown you research today that wasn't done by my group. It's done by scientists all over the world that are chasing this big goal, because they can see that the next generation of chemical technologies needs to be more sustainable, must come from either biological or CO2 based carbon feedstocks. And so there's a real grand challenge out there, and there's a real prize for researchers in this space, in this green tech space, and the race is on really internationally for everybody to compete on achieving this.
Brilliant, thank you both. So Chris is asking again, he's a fellow chemist, as you may be able to tell. But so he does ask the question, can we produce synthetic chlorophyll for converting CO2?
Yeah, so synthetic chlorophyll. So, okay, caveats. First of all, I'm not a real biologist. Our catalysts are inspired by biological systems, and I ought to watch what I say with you know, alumni in the room who may have a lot of biological know-how. But as I understand, photosynthetic plants basically, like they are like factories. They have multiple reaction sites and gas channels, and it's not a simple case of just, if you isolated chlorophyll and use that as a catalyst, we could just then use it in a lab as a catalyst, or scale it up to an industrial scale just by using chlorophyll. So it needs all that machinery around it. It needs you know, all the sophisticated evolved technology that a plant has in order to fix carbon dioxide and turn it into the hydrocarbons. We have someone in the chat who did biochem as well. So yeah, unfortunately, it's not a simple case of just isolating chlorophyll as the ideal catalyst for photosynthetic conversion. There are labs, particularly in California. There's the Joint Center for Artificial Photosynthesis, which have some kind of artificial leaf technology, which looked really impressive, but they really struggled to scale that stuff up. So they could show it on a lab scale, which was impressive. They published some nice papers, but then nothing happened for the past 10 years in that space. And that really shows, just because you can demonstrate something on a small scale, taking it up to something that's ultimately useful on a scale that we need for our everyday chemicals is a serious challenge.
Brilliant, thank you, Sandy. Well, we are approaching 7 o'clock, so I'm going to start to bring things to a close. But Chris, who's asked those few questions, he was here, studied chemistry in 1966 to 1969, and he did say at the start of the event that he would really like to be kept up to date on the chemistry centenary celebrations in 2025. So I wondered, Sandy, if you could just round off the evening by telling us a little bit more about that. What the plans are, and sharing that with the attendees tonight would be a good place to finish, I think.
Yeah, wonderful. Yeah, that's really great to hear, and done a few of the in-person alumni events. So 2 weeks ago, we were in the Botanic Gardens doing a similar talk, and there were a group of chemistry alumni there. And every now and again, we just see groups of alumni walking around the George Porter building, you know, coming for a weekend away in Leicester, which is always great to see people coming back to see where they were at uni and had great times. So I'm leading the centenary event campaign and the centenary event in spring 2025. So I'll put my email address in the chat. Otherwise, you can just find me on the University of Leicester staff pages, Sandy Kilpatrick, or indeed you can go on my group's website, which is kilpatrickgroup.uk. Let me just write that in the chat. So what we've got planned for the centenary event is it's going to take place here in the George Porter building. We're going to have Peter Atkins, as I said. Many of you have bought his textbook over the years. I certainly have got a couple of copies of Atkins Physical Chemistry, Atkins Inorganic Chemistry, and they're not just used as doorstops. I still do use them every now and again. We're going to have Josh Smalley, who's a chemistry alumni who's currently on the Great British Bake Off. Those of you who watch this series of GBBO, you'll notice there's a researcher from the University of Leicester that we share a lab with. And Josh will be giving a talk about the chemistry of baking. So that's going to be really fun. We make ice cream with liquid nitrogen. So there'll be lots of things you can eat, in fact, based on some of the chemicals that we have here, but all safe and edible. We're planning a really fun day for all the family. So I'll keep everyone in touch. We have a LinkedIn page as well for University of Leicester chemistry alumni. So if you join the LinkedIn page, I'll keep posting updates as we firm up our plans going forward.
Brilliant, thanks, Sandy. So yeah, there are a couple of comments coming through for you there in the chat, which I'll let you have a look at. But yes, by all means, obviously we'll keep all of our chemistry alumni up to date through our channels as well about that event and anything else that might be of interest, obviously. But yeah, we're looking forward to celebrating that special centenary with the team here. And our very own celebrity Josh soon. So that pretty much then brings the evening to a close. So I just want to say again, huge thanks to Sandy and to Hannah for taking the time to talk to us all tonight. I found it really interesting, and I hope everyone else has too, and that you've enjoyed the evening. Thank you all for joining us too. As I said at the start of the event, if you could give us some feedback through the event evaluation form, we would really appreciate that. It really helps us to make sure that we keep improving on these events and making sure that they remain relevant and enjoyable for all of our alumni. So it would be great if you could do that. The link is already in the chat there. I can see Kelly's popped that in there. So that's all from us then, I think. So I'll say goodbye and thank you very much all for attending, and we hope to see you at another Festival of Change event in the near future. Thanks very much, everyone.